Yeah, the next topic is finding the endpoint. As in acid-base titration or complex metric titration, uh, finding endpoint can be done by redox indicators. Okay, so our redox indicators are also dye molecules that change colors depending on their oxidation state. Okay, the acid base indicators are themselves also acid, act as acid or bases. Okay, likewise, the redox indicators themselves are undergoing redox reactions. In other words, they accept or they lose electrons, like this one. Okay, and this indicator, and when oxidized, it has a certain color, and when it is reduced, and the color changes. Okay, there are a lot of those species. Okay? So since this is the electrochemical reaction, so we can write the next equation for this one. Okay? So E equals E0 minus this part. Okay, and here is an example. This is ferroin. Ferroin is a organometallic compound with this part. Yeah? Uh, this is what? I forgot. I'm sorry. This molecule. Yeah? And then in ion, trivalent ion are complexed with three of this molecule, and it takes a pale blue color. Okay? And when it is reduced by accepting one electron, and the color changes, okay, to red. And the ion oxidation state is +2. Isn't it amazing that only one electron coming in and coming out of this molecule, yeah, changes color? Okay, yeah, it is very very remarkable. Yeah? Why? Because the electrons now undergoes electron transition, right? And then electron transition, the energy levels are different depending on this oxidation state. And here is a rule of thumb. This rule of thumb also applies to acid-base chemistry, and which is that when one of these compounds, the concentration is at least more than 10 times larger than the other form, and then color is dominated by uh, the compound of higher concentration. For example, when this ratio, okay, this reduced form in this concentration is more than 10 times than this one, oxidized form, and then color color dominated by this one. So the solution color is red. Okay, but when this form, the oxide form concentration is uh, 10 times or more higher than um, this form, and then the color is pale blue. Okay, but what about in between? The ratio between 0.1 to 10. Okay, and then intermediate color will appear. Okay, so here color changes over the range. So in this range, color changes. This is a transition color, intermediate color. Okay, yeah, this is a basic principle for the redox indicators for finding the endpoint. Okay, and not difficult. This list shows you different redox indicators depending on E0 values. Okay, so why it is important? Because when your redox titration, yeah, so when you think that the endpoint appears at a low of potential, like about 0.3 or zero point 0.4 volts, and then which indicator can be used? Probably maybe methanosopranin, or maybe indigo tetrasulfonate, or maybe methylene blue. Okay, but uh, uh, when you use, for example, the permanganate, okay, to oxidize something, right? And then which indicator is necessary? Yeah, since permanganate is a very strong oxidizing agent, so uh, at the equivalence point, the EGR value is very high, and then you may choose from this one, 3 is 2 prime by pyridinium, ruthenium, or this one. Okay, so if you choose other the compound as an indicator, and then there may be an titration error. Okay, this is a kind of guideline. All right, and there is a way to find the equivalence point with only several points before the before reaching the equivalence point. That is the grand plot. Okay, this grand plot is a general method to find the equivalence point. Okay, uh, yeah, but not using redox indicators in this case. Okay, the most accurate way I think is to simply follow, simply construct the total titration curve. Okay, and then you can locate the equivalence point. Okay, by first by taking the first derivative or second derivative. Okay, but that takes a long time. But there is a way to find the equivalence point, yeah, using several points only, yeah, maybe 4 or 5 points. But those points before the equivalence point, okay, the principle was already, you know, you learned in acid-base titration chapter. Okay? Anyway, let's take an example for this one, right? And this is the titration of this ferrous ion with oxidizing agent. Okay, and we use the reference electrode. Okay, so this part, this is must be subtracted out. Okay, because the cell potential is the difference between the indicator electrode and the reference electrode potentials. Okay, and here is their Nernst equation, and after you arrange this equation, you will you can reach this rather seemingly complicated equations. Okay, but if you take a look, and you will find this is not that complicated. Okay, here after rearranging this equation, then here the V is what? V is added standard solution volume. Okay, and E is the measure the cell potential. Okay, the VE is equivalence point. Yeah, you don't know yet. Yeah, and here and everything else is the same, and N is the number of electrons, right? And take this part is Y. Okay, and this V, take this V as an X variable. Okay, and then this is a simply Y linear equation. Y equals B plus mx. Okay, this is m, this is slope, and this is y-intercept. Okay, so plot v versus this one. This one, taking this one as y. Okay, then you can plot. So from the x-intercept, oh, this is x-intercept because not y. Maybe x is 0. Yeah, this part comes 0. Yeah, must be y-intercept anyway. Yeah? So from the intercept, you can calculate this one. Okay. Yeah, here is an example. Yeah, it must be y-intercept. Okay. No, 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 no. This is x is 0, and here x is let me see. Intercept. Oh yeah, yeah. This is E0 is a y-intercept. Okay, y is 0, and then this part is cancelled out, and then we get this part only, right? But also, okay, maybe x-intercepts x is 0, and then this one we can obtain, and then we calculate v times this part. Okay. Anyway, here is the y-intercept. Okay, y-intercept is here. And let me see. This is x-intercept here, right? When y is at 0. Then from this one, this is the equivalence point. Okay, but here you must be careful. Okay, these points are what? Actual data, right? Experimentally determined data points 1, 2, 3, 4, 5. All right, but yeah, look at that. Those points are before the equivalence point. If you uh, what add, for example, 20 milliliters of standard solution, okay, and then the point must be here, and then this doesn't show the linear line, but it bends around the equivalence point like that. So important thing is that find the several data points that shows the linear line, okay. Mm. Although you don't know the equivalence point, that doesn't matter actually. Yeah, you add more and more standard solution, and then you will see this curve looks like this. Yeah, it will bend like that, right? And then you take only this linear part, okay, and then extrapolate to find this x-intercept. Yeah? This is how the gradient plot is being done, right? Let's stop temporarily here.